Edie. Thank you.
Associate Professor of Applied Physics, I think it said. Associate Professor of Applied Physics and member of the lab at Stanford University. Darpa forward, advancing the horizons of national security.
Thank you. So today I'm going to talk to you about some really exciting things that have been happening in quantum engineering and quantum information sciences. And I'm going to start by asking you to do something that the speakers don't ask you to do typically, which is to look at your phone. So the phone that you have in your hand, it's jam-packed full of sensors, and these sensors are essential for the phone to understand its environment.
These sensors are essential for the phone to understand its environment. While I appreciate his JPEG there, sensors are everywhere. I have a better one that I've shown the synergist multiple times. There's an example of all the sensor systems that are inside your phone. Additionally, it's one thing to show you that image and say, yeah, look at all those sensors that we have in the phone, okay? It's another thing to take you into the taxonomy of biological signals for each individual sensor on that phone. And these biological signals are put into databases for human activity recognition radar. Human activity recognition radar. Horror. Can radar detect a human? By using UWB radar. What's that? The radar cross-section, RCS, of a human body and external body part motions, such as walking and hands and feet movements, can be detected. Oh, what is UWB radar? UWB radar? Ultra-wideband radars are radars that use ultra-wideband technology. What is that? Well, it looks like it watches you in your house, doesn't it? Sure does. Looks like it can go through walls. Sure does. Human activity radar. Wow. With the ultra-wideband, huh? Lots of different uses, including medical. Of course. Medical applications of ultra-wideband. Well, let's take a look. Where are we now? Hang on. Faculty openings. In computer science, and engineering, graduate programs that make an impact at McKelvey School of Engineering. Oh, I guess it's not a blog, huh? Nope. And I guess it's an actual school of engineering, huh? Yeah. Crazy like Cambridge. As an emerging technology, ultra-wideband wireless communications provides a very different approach to wireless technologies compared to conventional narrowband systems, which brings huge interest in it. Because of this, ultra-wideband has many potential applications to be researched. Key words: ultra-wideband, medical application, medical monitoring, medical imaging. Oh, look, it's a Yeti. Yeah, patient medical monitoring. Now, the synergists are familiar with the ultra-wideband, not only in our college textbook, but because it is ubiquitous. It's the big one in green over here. It's for everybody. Thus, human activity recognition radar are tethered because it's everybody. It's generic, right? in case you didn't know, yes. It is mandatory. It is allocated for packets in the medical monitoring systems with high cyber biological security. Okay? So, when we look at ultra-wideband radar with human activity recognition radar, with the taxonomy of all these biosignals, then maybe now we can go back to our video where the Darpa Associate Professor of Physics is explaining to you that the micro electromechanical systems, let's define that quick as well, so you know what those are. You do, but I haven't talked about them in a while. Micro electromechanical systems is the technology of microscopic devices incorporating both electronic and moving parts. Okay? Combines electronic and mechanical components to create devices like sensors, valves, and gears. MEMS devices are made up of components that are between 1 and 100 micrometers in size, and the devices themselves are typically between 20 micrometers and a millimeter in size. Wow, that's pretty small, smart dust drivers with your beam steering, isn't it? MEMS devices are used in many applications, including, what's it say? Wow, wireless communication, huh? Incredible. Circuits and systems, automobiles, aerospace, what else? Yeah, medical devices, fitness trackers, game controllers. Amazing. So now, back to our video.
They have to be small, they have to be very low power. And one approach that engineers have developed for realizing these types of sensors in the last few decades is something called the microelectromechanical system, or MEMS. And so here's some SEM images of a few of the sensors. These sensors sense everything from pressure to which way you're pointing your phone to how many steps you've taken. These are all in there. And so it's not just for phones. These types of sensors are what enable a lot of drone technologies, as well as all sorts of technologies that are important for national security, such as.
So the micro electromechanical systems are everywhere. They're ubiquitous. And they not only work with where you point your phone, they also work with national security and drones.
Thermal imaging.
Thermal imaging.
Now, there's a separate story, which is that of quantum sensing. So far away, not so far away, about 100 kilometers or 100 miles west of here, physicists and astrophysicists, they developed LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And this is the most sensitive sensor instrument that's ever been created by mankind. So they weren't.
Oh dear Lord, let's go there too. Laser interferometer. Oh boy. Laser interferometer. What are you? Calibration. Interferometry is a technique which uses the interference of superimposed waves to extract data. Aim and fire, baby, and measure. Oh, wow, that's amazing. Hang on, gravity gonna be involved. Just a second. Gravitational wave observatory. Okay, hang on. So it says measurement. For those of you that keep lying about this, we can't measure it. It's is it a particle or a wave? I don't know. Why don't we ask somebody underground who's working at Lawrence Livermore, or maybe we could go on over to Schaumburg, Illinois, and hang out next to the Fermi Lab. But I'll bet you they got an answer. Hang on. So gravitational observatory, gravitational wave. What's that? They're transient displacements in a gravitational field generated by the relative moving of gravitating masses that radiate, radii people, Morse math, outward. Gravitational waves are transient displacements. Do they affect humans? Strong gravitational waves are, in effect, time-varying tidal forces. A low-frequency gravitational wave that's strong enough would therefore be felt like a force stretching your body in one direction and compressing your body in a perpendicular direction. Oh, but they don't use those. Well, they just got done telling us that we're headed to Ligo, which is the second click away where the Caltech frauds hang out. Then we get to go to space.com. LIGO gravitational wave detector breaks quantum limit to find black hole collisions. October 2023, space.com. Okay. So, we're looking out in space with our laser interferometer gravitational wave observatory, and we're looking at black stars and black holes. Okay. Bullshit, but whatever. Because these perpendicular waves and gravitational waves are part of how we create the motion of our tectonic plates. They have an earthquake machine! Yeah, we control all the particulate in the atmosphere too, isn't it fun? Flux density, what's that? Electric flux density is the measure of the strength of an electric field at a given point. Oh. You know, if we're going to play with gravitational waves and we're playing with electricity, we better have an appropriate mathematical way to do that with a region of interest and precise targeting. And we do. Then we have weakened areas of the Earth's surface. We can use a little magnetic flux with that too. Electrical and magnetic. Oh. So what does all that have to do with your interferometry of laser systems, in which you're able to take all these measurements? I wish to draw your attention back. Measurements of how the signals, advanced signal processing technology, is helping them understand particulate at the micrometer level. You heard me. A millimeter in size and onwards to the nano, I guarantee it. Beam steering and beam forming, driving all these little sensors in the air particulate. Oh, why are they putting metals in the air? Well, if you understood plasma polaritons and polarity of how they're playing with all these systems of pushing cellular states back and forth outside the desire of the atmosphere because it's external stimuli, then you would be a little more averse to just sitting there going, oh no, they love us. Watch this.
I'm trying to count the number of steps that you're taking. This sensor actually detects whether black holes smashed into each other hundreds of millions of light years away. And it's a kilometer scale sensor, so it's much larger than what you have in your phone, but that's not the only thing that makes it distinct. The other really special property of LIGO is that it uses quantum mechanical properties to increase the sensitivity. So all sensors, both LIGO and the ones in your phone, if you use them kind of a naive way, they're fundamentally limited by something called the standard quantum limit. So, for example, if I'm trying to sense the position of this red block here, my instrument will result in a voltage that looks like this. And now, if something causes this red thing to move, it could be a gravitational wave, it could be you picking up your phone, or it could be a protein landing on a mechanical system. That red block moves, and now when I try to detect its position, I get a slightly shifted signal.
He just mentioned a protein landed on a MEM. I want to see that. A protein lands on a mem. Yeah, good luck with that. Hang on. Let me do it a different way. Protein folding with MEMS, not memes. So the reason that he mentions that, no doubt in my mind, alpha AI, protein folding, DNA origami, and that has to do with changing out things inside your cell structure, like E. coli and endoplasmic reticulum recombinant proteins. Protein folding and conformational stress in microbial cells producing recombinant proteins. If you're going to be changing out the cell structure in vivo, in place of origin, you're going to have protein folding, nucleic acid access, recombinant protein folding and misfolding, and E. coli biotechnology. And we change out those bacterial biosensors between E. coli and other bacteria that we naturally have in order to affect the gut microbiome for the Internet of Behaviors, for example. But we use it for good. Whatever. You're using it. That's my only point. You call it good, you call it bad. I call it a tool of DNA protein folding, which they often call DNA origami. A technique that folds DNA into those 2D and 3D manifolds shapes at the nanoscale to manipulate the cellular state. Use CRISPR-Cas9 to put DNA and RNA and anything else. They want to screw with your cellular states by opening the cell's surrounding protective shell and then extracting what they want, putting in what they want. Medicine and dentistry, material science, nanotechnology, chemistry, physics, and computer science. DNA origami can be used to create devices that sense, compute, and actuate. That last one there is where it makes the physical change. That's why you have so many images, and we here on the channel have so much software with your Lego bricks and your bio bricks, all the different types of open source software that they use with things like the Department of Energy's gold system to log in and out of omics. In case you forgot, because we've gone over this a few times, omics is all of your biology, DNA, RNA, proteins, metabolites, the study of the entirety of the specific factors within a cell, tissue, or organism, omics. It also refers to the tools used to analyze DNA, RNA, proteins, or metabolites. Then I click on images. We'll be here all day. Nature, genome-wide association study, frontline genomics, multi-omics integration, ResearchGate, omics and technology for evaluation of your seq RNA, your mRNA, your CRISPR-Cas9, and all the different ways we're using precision AI healthcare with phenotypes. Omics, OMICS. DNA, RNA, amino acid chain, protein, metabolome. Remember, metabolomics sounds like Manola Blahniks. And genomics addresses processes at the level of DNA. This can include identifying species, genetic stock identification, and inbreeding. Transcriptomics focuses on RNA transcribed from genes, stress responses to the environment, health concerns, and cell dysfunction can all be examined. RNA and amino chains, transcriptomics. Let me zoom in for you a little bit so you see where I'm reading. Proteomics deals with the proteins produced after RNA is translated. This can be used to explore immune function, reproductive fitness, and mechanisms of stress response. And metabolomics refers to the measurement of certain molecules produced in the cell. Metabolites are involved in many of the biological functions of fish, especially that result from the environmental effects. Oh, that's back to that quorum sensing at Rice University, where they started with the water. Yeah. Here's another one. Frontline genomics, transcriptomics, proteomics, metabolomics, lipidomics, epigenomics, interactomics, phenomics, ionomics, Genomics, omics. And where are you used to seeing this on the channel? The Agenda 2030 goals none of you will admit to for the biodigital convergence. Oh, you're kidding. No, I'm serious. It's another reason why I get so frustrated with the professionals who gaslight professionally. These are jobs. Very important jobs, too, because they're insulating our biosphere with all the changes they're making to the environment. Now, these underground laboratories where CERN is housed, in part with MITRE and tokamak and all of them, that's why we're going this direction. It's taking me a lot of context education because I'm really tired of your narrative drivers getting to provide ad hominem attacks instead of debunking what I'm going over so that people who are serious about this research can look into cognitive science, including cognitive neuroscience, information technology, including advanced computing, biotechnology, biomedicine, including genetic engineering. Yeah, it's a 20-year-old concept. Isn't that great? You're paying for it with your tax dollars for 20 years, and you're still claiming it's theoretical. That's hilarious. That's a butt ton of money for being theoretical, and that's not all. We're going to go to Cambridge shortly. So, as one of the many universities and people who are working on this. So, where do we find omics? Gee, I don't know. Let's take a look at the biodigital convergence here with the IEEE and IEC and ISO standards in red. And you tell me if you can find omics, genomics, microbiomics. Just let me know. See if you can find it. I'm going to give you a hint. The nanotechnologies are at the top. The engineering is at the bottom. Informatics with computational biology and those biosensors you won't talk about, that's on the right. What big black word that starts with the letter B as in bullseye do you see on the left? Biology. Yeah. And then do you notice where the omics are? They're next to biology. Need me to define that for you too? Maybe. What is biology? Especially these days, right? Okay. Biology is the scientific study of living organisms encompassing their structure, function, growth, evolution, and distribution. Wow. So how many of you out there don't know that biology is a science? How many of you out there, honest to goodness, have no damn idea what biology even is? Come on, people. But let's say that you don't. No, really, I'm serious. Let's say that you're like, okay, well, I know that biology is the study of living organisms, i.e. humans, animals, microorganisms, and plants. Okay. Do you know what biomedical engineers do? Well, what's that? Well, that's a biological medical engineer. Okay. So why are they special? Well, they log into your body to actuate those sensors. That will create a physical change for something called telehealth and mHealth and eHealth. Excuse me, that's mobile health, where your doctor can pull your biomarkers from far away so that they can take a look at what's going on. Telehealth is here to stay because the COVID sparked a long overdue telehealth revolution because we've got 30 years of biosensors already. Did you lie to people about the body being electrical with direct current in the human body, being a circuit of resistors and capacitors? Did you lie about this? This is more measurement of electricity and that galvanic coupling, bioelectricity. Yeah, did you mention that to people, or did you tell them that they could click their heels and jump timelines? Did you lie to them about their own anatomy so that you could force them into a religious setting of some kind? Maybe you made them put a robe on and you told them they were magical while you were hitting your little terahertz button on your phone. You're saving the world, remember? You're the electrical engineers that have built these systems out for years. So, biomedical engineers work with the biosensors under the skin, inside of the in vivo networks, like the intra-body network, intra-body communications, worked on since 1996. And so here we have the sensors and the radio frequency sync. We got some magnetism going on that crossbar section of body radar, human activity recognition radar. And then with the transmission and receivers, see, when I show this to people, they always think the same thing. It's a wearable. Nah, it's an air molecule known as a MEM. When you accessorize for your day, are you imagining yourself wearing your air molecules as you walk through them? No, but they are. See, that's kind of the problem here with biomedical engineering. We're using advanced signals processing to measure biosignals. Yeah, it says pattern recognition and machine learning for biosignal data, neural networks, multimodal speech and audio, monitoring and telemetry, frequency analysis and wavelet transform. Yeah. So you got to wonder, these are jobs. These are people going to work. These are people who are biomedical engineers, and they're using biomedical signals, okay, that they can log into in the body with these sensor systems. Pardon my dying iPad. And biomedical engineering, okay, biology, tissue engineering, artificial organs, cellular biology, bioengineering, electrical engineering, electronics, robotics, signal and image processing, chemistry and biochemistry, biotechnology, materials chemistry, drug delivery, physics, biophysics, biophotonics, biomedical optics, medical physics, radiology safety and nuclear medicine, clinical professionals, problems to be solved in clinical trials, computational biology, bioinformatics, artificial intelligence, and telemedicine. Mathematics, optimization, statistics, softwares, simulations like the IITSEC with the Department of Defense for 50 years. Materials engineering, biomimetics, biomaterials, mechanical engineering, prosthesis, biomechanics, there's that modeling and simulation again, microfluidics. So now that we know that's a job, yep, and we understand, oh, okay, so we've paired biology with technology for all of our wearables and our apps and all these things. Yes. So how does it work? How are they logging in and out of your body? Well, they're using your human biofield, because that's a biological field. And they're logging in and out with their omics. They have software for that called Synthetic Biology Open Language for their biobricks. And the way that they're rebuilding all these standards inside of you, in vivo, just rearrange your DNA, your RNA, and anything else they want to with Python nerds. Watch this. I warned you. I said genetic circuits that have been worked on for decades. What'd you tell people? The aliens are here. Okay? So we have synthetic biology open language in which we get to design the DNA component, play with the code, and then we have database collections and aggregate, and then we've got tons of drop-downs and different universities that are working with the way CRISPR-Cas9 and the rest of the omics function in order to actuate a cellular change under your skin remotely. And due to the fact, and it is a fact, that when I come in here to show this stuff, don't worry, our video is not too long, it's only 6 minutes, but everybody's still screwed up way back here in the beginning. You have a phone that has a bunch of sensors on it. No, not me, the DoD left me out. Then we have all these underground systems that are running massive, like he told you, types of MEM energy through the atmosphere playing with the particulate. He didn't say it that way. Good, I'll click play. This time I'm going to let it play to the end. Let's see what he tells you.
Observatory. And this is the most sensitive sensor instrument that's ever been created by mankind. So they weren't trying to count the number of steps that you're taking. This sensor actually detects whether black holes smashed into each other hundreds of millions of light years away. And it's a kilometer scale sensor, so it's much larger than what you have in your phone, but that's not the only thing that makes it distinct. The other really special property of LIGO is that it uses quantum mechanical properties to increase the sensitivity. So all sensors, both LIGO and the ones in your phone, if you use them kind of a naive way, they're fundamentally limited by something called the standard quantum limit. So, for example, if I'm trying to sense the position of this red block here, my instrument will result in a voltage that looks like this. And now if something causes this red thing to move, it could be a gravitational wave, it could be you picking up your phone, or it could be a protein landing on a mechanical system. That red block moves, and now when I try to detect its position, I get a slightly shifted signal. And as you can see, you can see something that's happened, but the noise there kind of hampers your ability to really understand what's going on. And in quantum mechanics tells us that basically this noise scales as 1 over square root of p. Now LIGO actually circumvents this limit. It uses quantum states to achieve what's called the Heisenberg limit, where now your noise scales as 1 over p. And this allows LIGO to observe 10 times more of the universe than it would be with a 4-kilometer long antenna. And so how do we bring these two stories together? How do we bring some of these advances in quantum sensing into sensors that are actually deployable? And in the last few years, there's been actually a significant amount of advances in that field, and there's a lot of exciting things happening. So here is here's a picture, a PowerPoint picture of a set of mechanical resonators. They're very small. They're nanomechanical resonators, roughly the size of a coronavirus in some dimensions. And they oscillate at a few gigahertz, and we can make tens, hundreds of thousands of these on a chip and address all of them simultaneously. So we can make these types of sensors, but actually the hard part is the readout electronics. So the cell phones, the sensors that you have in your phone, they use classical electronics. So they use transistors, that's kind of the basic unit. And the problem with transistors is that they don't preserve quantum coherence, they don't preserve quantum information, and so we can't use transistors. So luckily, there's been a huge effort trying to develop quantum computers, and these microwave circuits use Josephson junctions instead of transistors, and there's a number of companies now building these things and scaling them up, and these are the types of electronic systems that we'll have to use for the readout. So where are we? We've been able to integrate these sensors with qubits, with these superconducting quantum machines. And we've been able to make measurements that are actually classically not allowed. So for example, here we can see single quanta of sound in one of these devices. We've also been able to engineer quantum states of these devices and engineer entanglement between say, two of them that are side by side. And that's kind of the fundamental resource you need to achieve that Heisenberg limit. And in the next 5-10 years, there's a lot that's going to happen. I think we're going to be able to, in my lab, we're working on trying to use these types of quantum sensors to sense proteins. We're trying to build quantum memories out of them. We're trying to build a quantum modem to connect these machines over long distances. So, thank you.
Well, there's some terminology there we'll be going back to. But it looks like they're doing fine. Where are we at? A year ago, Darpa TV again. Wow. So, when it comes to the tomography and the measurements and all these different interferometry and the variant systems, our human bodies are involved in all of this. That's how they are pulling mega amounts of data. That's why it's a biodigital convergence. That's why it's a network-centric system. That's why there's so many different types of sensors. Okay? It's also why when they pair the graphene on a substrate and can do really creative things, that we should be honest about where we're at with the ultra-wideband and the Internet of Medical Things in order to propel the Agenda 2030 and C40 goals that are already finished for 2030 with remote patient monitoring, behavior modification, watching you under the skin 24/7 for ubiquitous health monitoring for your health. Health monitoring is for your health. how. And if you don't know how, then how are you being responsible for your own health? Well, I'll put my wearable on, I'll slap my Fitbit on, and then they get to override what your cellular structure is doing under your skin. Oh, that's impossible. Not me, because you refuse to admit that your body is electrical and accessible to other human beings, not aliens, who have jobs as biomedical engineers with circuits and systems like the MEMS. Yep. And now the synergists know exactly where I'm going. What's this? 2023 IEEE Biomedical Circuits and Systems Conference. Whoa. So Darpa TV is telling you they've achieved this, and phononics is in their tomography. And yet in 2023, here they are at a hotel. It's all done. And they get to meet for a 3-day single-track program of biocast, multidisciplinary with topics like biosensor devices and interface circuits, body area sensor networks and wireless health monitoring, implantable and wearable health devices and systems, bio-inspired and neuromorphic circuits and systems, electronics for neuroscience, innovative circuits for medical applications, biofeedback, neuromodulation and closed-loop systems, rehab, biotelemetry, and energy harvesting scavenging circuits and systems, lab on a chip, bio-MEMS, and point of care. What's that? That's when you get a phone that has access to our beam steering for all those teeny tiny little particulate in the millimeter wave terahertz. It's all for your health. Then they hit a button on your phone and they can access your biosensors with software like Bioconductor. And Bioconductor is oriented towards different types of microarrays, and as you can see, BioMEMS is on the top, Organ on a Chip is on the left. This is open source software, Linux Swiss cheese, your favorite. Miniaturized biosensors is on the right, and yes, it's Mac and Windows as well. But y'all on the back end, Unix and Linux are very good friends. So your Linux Swiss cheese has been in the back end for all the back doors. And the code nerds like to pretend, well, I'm watching my operating system, I'm a programmer. And those of us from networking will walk right around you with protocols that watch you without your software knowledge. That's why Linux is their favorite. Talk to me about your kernels. Here we go again. Artificial intelligence of things for healthcare, biomedical imaging and image processing, biosignal recording processing and machine learning. Here we are, genomics. There's our omics, and systems biology, human-machine interfaces, medical information systems, and bioinformatics. Emerging technologies, flexible devices and circuits for biomedical applications and brain-computer interface. Wow, amazing. They get to go to a hotel and discuss it like adults, and those of you on the X get to lie like frauds. Boy, that's weird, isn't it? Don't we want to talk about what Darpa TV is on about? Mark 536, amen.